I'd like to talk a little bit about efficiency for a change, and also use that to introduce a new programming technique. Not a new language concept, perhaps, but a new programming technique. And as my prime example, I'm going to use the function reverse. So I've shown that here again. This is the version of reverse that we had introduced in a previous video, which follows the standard design pattern on lists exactly. It has a pattern match on the incoming list. It has a case for the empty list where it says the empty list is returned. In the cons case, we make a recursive call on the tail of the list, and then we discover, oh, in order to go from the reversed tail of our list to the reversed complete list, we have to append X to the end of that reversed list. And I had hinted at the inefficiency of this approach even then, because the append function itself has to traverse the entire list, and we do this in every step. So if the list is very long, we have to traverse several really long lists in order to compute the reversed list, and that leads to overall a quadratic time complexity. By now, you should ideally also have done the exercises that actually give you the assignment to define a more efficient version of reverse yourself. So we're going to recap that now, and also put it a little bit into context and see what the underlying technique is and where else it possibly can be applied. So first of all, let us observe as a baseline, just as a subjective baseline, how fast or slow this version really is. So, I mean, certainly if we call the reverse function that we have now on relatively small lists, everything seems totally fine, right? And of course, even for what we're about to observe, we always have to take it with a grain of salt, because we are working in GHCi here on the interpreted version of this module. If we do a full compilation, then everything will be faster. But here we are talking about a complexity class. We're talking about the fact that the algorithm is quadratic rather than linear, what it should be. And that will always make a difference eventually, right? I mean, even if optimizer makes the code faster overall and the compilation makes the code faster overall, the quadratic time complexity will not go away. We'll still have the same problem. So let's do a substantially larger list. Let's take, say, 10 million raw elements, okay? And now I hit this. And now see that we have to wait for quite a bit, right? Nothing happens at first. And then suddenly we get one element, and then we get the next elements, and they come slightly faster, but there is an immense delay between any two elements that are printed. You can see lazy evaluation in action here, because it's the printing of the result that is driving the evaluation, and we get interleaved printing and result computation, right? So we see the results as they appear, right, rather than having to wait for the complete list to be reversed before we see anything. So that is good. But we also see that coming up with every single number here is a pain, apparently. Every single number costs a lot to compute. And this is exactly this phenomenon that I have been describing before, that, right, in order to come up with the first element of the reversed list, right, see, the first element of the original list is 1, right? So we hit this cons case. Let's do equational reasoning, right? So if we have reverse of 1 to 10 million, right? Don't worry, I'm not going to do the entire introduction, the entire reduction. Then this is essentially syntactic sugar for something that starts with 1 cons, and also this enumeration is lazy. So I mean, we'll have basically to compute the result from 2 to 10 million still, right? And at this point, we get reverse, the second case matches, right? So we get reverse of 2 const 10 million plus 1, okay? So now we have to compute another call of reverse 2 to 10 million, and we have to do this traversal, right? So not only do we have to compute all this, and in order to compute all this, we have to compute the reverse call from 3 to 10 million and 4 to 10 million and so on and so forth. We also have to do this append before we ever get at the first element of the reversed list. And this append, right, still has to do like a full traversal of the reversed list that comes out of this, which is very, very long, right? So before we even see the first element, we have to wait really long, because we have to build up this whole chain of reverse calls on and on and on. But even then, between every 2 elements that can be printed, we have to perform one such full traverse call, append call, which will traverse a very long list initially. This will become faster over time, right? Because the closer we get to the end, the shorter the lists that still have to be traversed here to append the elements become. So basically, this is very slow in the beginning, which we are at the moment. If we would wait long enough, it would eventually speed up, right? If we do a slightly smaller list, we may even be able to observe the speed up. So if we take 1 million only, then we don't have to wait quite as long. And now it still takes quite a while, right, for one line to fill up, right? And I think it's still too slow to wait for it. Perhaps see if we can go to 100,000, but then perhaps we don't really see it anymore. But we still see that, like, perhaps there is about 1 second for one line to fill, right? And now if we get further along, then it becomes a bit faster, right? And if we go towards the end, it should speed up quite considerably. I'll leave this running for a bit while I'm going to continue to talk, so that hopefully you can observe that it becomes faster over time. So intuitively, we shouldn't have to do this. We shouldn't have to do this repeated append calls. And but this is an algorithmic problem. This is a problem of the algorithm that we're employing in order to reverse a list. In order to reverse a list, and we have these list structures that are asymmetric. So you can look at a list as a stack, essentially, or perhaps a pile. Imagine you have a pile of books, and you want to reverse that. A pile of books on your table. You want to create a pile that has all the books in reversed order, right? And what we're basically doing is that's the algorithm that we're currently implementing. We're taking the topmost book from the pile, then we are recursively, so we're keeping that somewhere in our hand or somewhere, right? Then we're recursively reversing the rest of the books, okay? For which we, again, have to take the topmost one, and if we have that, and then we're going to go through the entire pile and lift that pile and shift the book that we picked up into the very bottom, right? So that ultimately it becomes the topmost element that we originally had becomes the last element. So basically, we are taking all these elements of the pile, and then we're always lifting the whole pile up and inserting it in the bottom. And the pile is heavy, right? We have to go through all the pile. That symbolizes having to go through the entire pile and lift a potentially very heavy pile in order to insert the elements in the bottom. So if you had to reverse a pile of books that is on a table, you would probably not follow this algorithm. You would probably follow a different algorithm, namely hoping that there is a little bit of space. You would take the topmost book and put it into an empty space, building up a new pile right next to it. And then you would take the next book and put it on top of the first book that you have just placed there. And then you take the next book and put it on the other pile. And you would just repeatedly put books from one pile to the other, and when you're done completely, you have like the original pile is empty and the new pile is complete and it has all the books of the original pile in reversed order. And it's very easy to see that this algorithm is linear, right? We are going through the pile once, we're moving books from one pile to the other, we're having every book in hand exactly once, and we're doing a constant amount of work with every single book. So perhaps we can implement this algorithm. So for this, I'm going to introduce a different function, and that is also, again, closely related to what you had to do in the exercises. I'm going to call this reverseAux for auxiliary, and I'm actually going to give this 2 list arguments rather than just 1. And the idea is that these 2 list arguments are symbolizing the 2 piles. Okay, so the first list argument is, let's say we have to make an agreement here, the pile we are creating. So this is the one where we are building up the result, and I'm going to call this the accumulator. Right? Accumulator because it accumulates the result. It holds sort of an intermediate result, the already built up partial reversed list of essentially everything that we have already seen. And then the second argument is what's left of the original pile. That's basically symbolizing the list that we still have to visit, right? The 2 things that are left. And from these 2 inputs, I'm going to create the result now. Okay, so we have the 2 pile scenario now. One which already holds a part of the list in reversed order, and the other which has the remaining books of the original pile, so basically the remaining part of the original list. Okay. Now we do pattern matching again, and we do pattern matching not on the accumulator, because the accumulator is, it's also a list, but it's not something we want to deconstruct. We want to operate on it. We want to shift more things onto it, essentially. But we want to we're looking at the remaining pile, right? And if the remaining pile is empty, we do one thing. And if the remaining pile is not empty, right, then we do another thing. Okay? So, if the remaining pile is empty, then hopefully, right, by that time, the accumulator pile, where we put all our books, has the complete reversed list. So in this case, we should be able to just return the accumulator, and that should hopefully contain the reversed list. And in the other case, right, that's our cons case, what we're doing in every step, we are taking the topmost book from the remaining pile and moving it into the topmost position on the accumulator pile. So that means we basically shift the thing from the one to the other, and then we're repeating the process. So we're making a recursive call to reverseAux, but now with changed arguments, namely that we move x onto the accumulator pile, right? And we are removing x from this pile. Okay. Now, if we look at this definition, it still follows the standard design pattern on lists, right? Look, we have two cases, one for the empty list and one for the cons. And we have a recursive call on the tail of the list in the cons case. So this very much follows the standard design pattern on lists. But of course, it operates at a different type, and it required an extra idea, right? And the extra idea was that we have to introduce this extra accumulator argument. And in fact, it also has a different type than the original function. So we haven't actually re-implemented reverse. We still have to think about how to re-implement reverse if we actually want to do it. So at this point, it is probably a good idea to reserve the name reverse for what's going to be the good version of reverse, and to rename this version of reverse here to be let's call it slow reverse. Okay. Sorry. Somehow I didn't do this in the right way. Sorry. Oh, okay. So this is our slow reverse function. This is going to become our good reverse function. So how do we implement this one? Well, all we have to do is we have to basically initialize the accumulator, right? We have to, if we want to reverse this pile of books XS, then we have to go into the situation of reverseAux, where we start out with an empty accumulator, and then we use the original pile as the second argument. And at this point, we can actually remove XS from the left-hand side and the right-hand side, so we can partially parameterize rather than fill up, because if we look at what's the type of reverseAux applied to the empty list, this is exactly, if we have supplied one argument, it's exactly list of A to list of A. So we can simply say reverse equals reverseAux of the empty list. Whether you put the extra argument there or not does not matter. Sometimes this transformation, whether you're putting an extra function argument as the last argument on both the left-hand side and the right-hand side or not doing it, is called eta reduction if you describe the process of removing it, or eta expansion if you describe the process of inserting it. It's just different viewpoints, right? You can say reverse is the function that takes an XS and then calls reverseAux with the empty list and that XS. But you can also say reverse is the function that arises from partially applying reverseAux to just the empty list. Okay, and once we have done that, we have the original function back. So now I have to abort my experiment here. Unfortunately, I think this is still too slow to really see it speeding up. I think it's unfortunately not so easy to get the right size. Perhaps, I mean, I can. Yeah, I mean, it's very difficult to see that it's actually speeding up over time, unfortunately. Yeah. So to find just the right size, but it does become faster towards the end. Anyway, now let's reload and let's try reversing our list of 10 million. Of course, this is still a list of a certain size, right? So it still, like, in order to come up with the first element of the reverse list, we have to traverse it once. But we should not then see that there is this long delay afterwards. It should then start printing rather quickly afterwards, because once we have reversed the list, it's essentially there. And now the speed is limited by the speed of printing, but you see it's going relatively fast. And printing is actually relatively slow. So, but we get to a result much sooner. And if I take a slightly smaller list, like just 100,000 elements, then we actually get to an end result rather quickly, right? And if we do this again with the slow version, then or the slow reverse, it's called, then we already see that this is significantly slower, right? We wait far more than just a few seconds here. So this is really making a drastic difference. Now, the only creative step that we have really taken here is to realize that we need this accumulator, right? That we need to reserve the space for building up the result. And then once we have made that creative step and initialized it to the empty list, then the rest basically follows the standard design pattern again. But this is an extra step. And it does bring us to the question whether that idea that we have just been using for reverse is also applicable to other functions that we have been writing already, or other list functions. And that's what we're going to discuss next, right? So we're going to look at other functions and see whether they can benefit from the same trick. And I'll take away part of the answer. We'll see that some functions do and other functions do not. And it's quite important to learn when to apply this trick and when not. And that's what we're going to do.